Hi kids, Smath here, and this is a continuing video that we're working on involving our unit on bonding. And today's topic, as you can see at the top of the notes, is molecule polarity. And the question is, why do we really care if a molecule is polar or not? And the question's really interesting because polar molecules will usually conduct electricity in solution. So you're not going to want to use a polar molecule to try to clean something that's electrical in nature, trying to clean up, video game contacts or computer contacts or copying machine sort of things. You're not going to want to use a polar. You're going to want a non-polar molecule to do that because it won't conduct electricity in solution. These polar molecules are also probably going to dissolve in water. And the reason there is water itself is polar. And so the phrase we use in chemistry is like dissolves like. So if I have a polar molecule and water is polar, the polar solvent water will dissolve the polar molecule that we put into it. If it doesn't dissolve, they're going to separate into layers possibly. It'll be like oil and water. Oil is non-polar. Water is very polar. So we really want to keep track of these polar molecules. In the pharmaceutical industry, we keep track of these things in terms of will they react with certain things in the blood that are both polar and non-polar? Will they react with certain hormones or with certain other neurotransmitters that we're looking for? So polarity of a molecule is very important. And it's relatively easy to determine if we've drawn the Lewis structure correctly. We have to draw the Lewis structure properly, or we're not going to get the polarity correct. And those two questions are always going to be enmeshed for us. Draw the structure. Okay, is that structure polar or non-polar? Or ionic? It could be ionic as well. And we're going to talk about all three of those situations. The easiest thing is to say, how do we know when something is going to be ionic? Well, a molecule is ionic if it contains an ionic bond. And at that point, we're done with it. We don't even mess with anything else. We've looked at the electronegativity difference and we've said the electronegativity difference was 1.7 or greater. And because of that electronegativity difference, we know that has an ionic bond. And if it has an ionic bond, it has an ionic molecule too, or it will be an ionic compound. We can't really say it's an ionic molecule because molecules by nature are covalent. So we would say it is an ionic formula unit instead. So our concern isn't whether it's ionic or not. It's about whether it's polar or non-polar. Ionics are pretty easy. You got an ionic bond, boom, you're done. So let's look at what conditions we need for a polar molecule. And there are three of these conditions that we need to keep track of. We'll go through each one here. So condition A is going to be the single bond. And what we mean by that is that if a compound has only one bond, then the bond type is going to dictate the molecule type. Here's what we mean by this. So if we look at H2, hydrogen gas, it's a diatomic gas. We know it has to exist like this. So we look at H2, and the only way to draw that really is an H with a single bond to an H, because each hydrogen only has one electron to it. So there's my hydrogen molecule. And if I look on my electronegativity table, you will always have the electronegativity table. So don't memorize, don't worry about that. That's always going to be out on your desks for you to use. It's in your notes, it's in the module. So you've got that. If we look on that electronegativity table, we find out that hydrogen is 2.1 and 2.1. And well, if we subtract those, 2.1 minus 2.1, then the eneg difference is equal to 0, which means we have a nonpolar bond. So what that means is those electrons are equally shared between the two hydrogen. There's no pull from one side or the other because electronegativity is the attraction of an electron. So since this is perfectly nonpolar, the electrons are evenly shared between the two hydrogens. There isn't a problem with charge. And since there's only one bond, this is also going to therefore be a nonpolar molecule. So this isn't going to conduct electricity. This isn't going to dissolve in water. This isn't going to exhibit any of those polar characteristics. This is nonpolar. Now let's look at another molecule. It's going to be a wee bit different here. If we grab now, instead of H2, let's grab HCl. Well, now I put my hydrogen there and I put one dot with it. And then I put my chlorine over here on the other side. And I go 1, 2, 3, 4, 5, 6, 7. And how convenient. Each one of these has a lone electron. And so if we make this bond between them, now the hydrogen has 2. That's the most hydrogen can have. Now we look at the chlorine. Chlorine had 7, right? 2, 4, 6, 7. And now it's sharing one more, 8. Now chlorine has 8. And when we draw a Lewis structure, we always want the more electronegative element to achieve an octet. So we feel pretty good about this Lewis structure. This should be pretty stable is what we're looking for. Now, if we look on our electronegativity table, now I've got hydrogen at 2.1 and chlorine is at 3.0. So the difference between those two, I've got an eneg diff, not just a value, but the difference between them of 0.9. So I have a polar bond. And we could even go further and say, oh, well, hydrogen has the lower value, so we could designate that as a partial, that's a lowercase delta positive. Chlorine is higher value, delta negative. Some of you are saying, well, wait, delta is a triangle. A capital delta is a triangle. A lowercase delta kind of looks like a swan neck, I guess. I don't know what it is. But now we know that it's negative. Another way we could show that is we could draw an arrow and put a little tail on it. And what that implies is the electrons from this side are being drawn towards that side. Now, how do we know they're going towards that side? Well, the electrons are always going to be drawn towards the element that has the higher electronegativity. So chlorine has a 3.0, hydrogen has a 2.1. The electrons are being pulled towards chlorine. That's what that high electronegativity does. And now, in this case, there's still only one bond, and that bond is polar. So what we have now is also a polar molecule. This will dissolve readily in water. This will react with electricity. It'll conduct a current. It'll do all sorts of things. So that's our single bond scenario. And that's a good one. That's just scenario A. If the compound has only one bond, then the bond type and the molecule type are the same. The next two get a little more complicated for us here. So let's look at B. Excuse me. Get my blue back. So B is going to be lone pairs. And I gotta clarify that. Lone pairs on the central. And what I mean is if there are lone pairs on the central atom. So let's use our words. If the central atom of a Lewis structure has any lone pairs, then the molecule is polar. Those lone pairs are going to automatically create a side of that molecule that's going to be negative. What we mean by polar is there is a separation of positive and negative sides of the molecule. So if there are lone pairs, that's like saying, hey, there's pure negative electrons right here on the central. That's going to make the middle of it negative, and that means everything else on the outside is probably going to be more positive. That's a polar molecule. So let's look at an example where this happens. The most basic is one that I've already alluded to in this video, and that's H2O. So I look at H2O, and I've got to draw this now. So if I try to draw H2O, I go, hydrogen can make one bond. Oxygen prefers to make two bonds. That's on my periodic table that we've written down a bunch of times. Oxygen likes to make two bonds. So I'm going to put oxygen in the middle. Oxygen has 6 electrons, and hydrogen has 1. And I like to say this, nature loves symmetry. So these molecules are going to try to achieve symmetry. How come? Symmetrical things are usually lower in energy. And that's pretty much what we're doing with bonding. So in this case, we're going to link together our hydrogen with our oxygen. Hydrogen gets a duet. Oxygen gets an octet. And if I look at the electronegativity values here, hydrogen is still 2.1, hasn't changed. Now, just because there are 2 hydrogen, doesn't mean anything. We just use that value. Don't multiply it and say hydrogen is 4.2. That's a bad idea. Oxygen, in this case, in every case, 3.5. It's the second most electronegative element on the periodic table. So what this means with my arrows is the electrons from hydrogen are being pulled in towards the oxygen. So what that's doing is the electrons from hydrogen are being pulled in, and the electrons from the oxygen are sitting there too. And so what we have here are polar bonds, because the electronegativity difference between these two is 1.4. That's below 1.7. So I have polar bonds, and because of the lone pairs on that oxygen, we have a polar molecule. Now, it said any lone pairs. So it doesn't matter how many. Here's another example for you real quick. We could do ammonia, not ammonium, not the polyatomic ion, but NH3. I take the nitrogen, 1, 2, 3, 4, 5. I put 3 hydrogens. Hydrogen, hydrogen, hydrogen. Oh, looky there. And now if we look at electronegativities, hydrogen is 2.1, Nitrogen is 3.0, not quite as electronegative as oxygen, but enough to draw the hydrogen electrons toward it. Couple that with this lone pair that's sitting up top. And again, 3.0 minus 2.1, I'm going to have a polar bond. I'm also going to have a polar molecule. And you're saying, well, gosh, that means they're always going to be the same. If it's a polar bond, it's going to be a polar molecule. And that's not necessarily true. Here's an example that's just like that ammonia that we did. But instead of ammonia, if I substitute that with phosphorus, pH 3, now the phosphorus goes in the middle just like the nitrogen did. It bonds the exact same way. Hydrogen, hydrogen, hydrogen. But now that we look at the electronegativities, hydrogen's 2.1 and phosphorus is 2.1. So in this case, we have a nonpolar, we have three actually, three nonpolar bonds, but we still have a polar molecule. And you're saying, well, could we have different types of bonds? Yeah, we really could. As a matter of fact, if we go C, let's do C, Br, H3. Now this looks really ugly, but we've got carbon written first. And anytime carbon's written first, carbon's going in the middle. Carbon has 4 valence electrons. It can form 4 bonds. That's the most that we're going to deal with, except unless we get to the 2 exceptions that we sometimes have to work with. So in that case, the carbon goes in the middle. And now it doesn't matter where you put things. Put the Br up top and put the H's down below. And this is a good looking Lewis structure. Doesn't matter where you put them. Remember, this is not 2-dimensional. This is a tetrahedral. Everybody is equal space apart. So if that's the case, let's look at our values. Carbon is 2.5. Bromine is 2.5. Hydrogen is 2.1. So what we have is a carbon to hydrogen bond that's 0.4, just barely. That's a polar bond. And we have C to Br, whoops, excuse me, which has no electronegativity difference, which is a nonpolar bond. And what I've done is introduced the third topic. All right. The third topic has to do with dipoles, symmetry, and canceling. So if we look at our arrows in this case, the hydrogen is pushing up, and pushing in, and the bromine doesn't have an arrow because it's nonpolar. This is going to be a polar molecule. It's not symmetrical. There are no lone pairs, so it doesn't work for A. It's got more than one bond. It doesn't work for B. There are no lone pairs. So now let's look at what is scenario. I keep doing that in red. What is scenario C? Scenario C says the dipoles do not cancel in a polar molecule. And that's what this means, is the arrows are my dipoles. They're the pull, the direction of the electron flow. And so I almost hate to personify it, but if we personify those electrons and we say, look at the forces on this, that there's electrons being drawn towards the carbon in the middle and nothing being done from the top. The outside becomes positive and the middle becomes negative. The phrase I use is, if we look at those arrows are actually vectors. Vectors have direction and magnitude. Would the molecule move? And in this case, that molecule would move. Now, the molecule isn't really moving. We're just using that as an explanation for the electron density. The electrons are moving towards the side of the molecule. So the dipoles here are not canceling, and that's what makes this molecule polar. Let's look at another example. If we take MgI2, magnesium can make 2 bonds because it's in the second column. Iodine can make 1 bond. It's in group 17. So I'm going to put magnesium in the middle, dot, dot. I'm going to put my iodines on the outside. Symmetry. Iodine has 7. Now at this point, we're going to use a dash. It's going to save me from writing a lot of electrons. A dash is 2 electrons. Don't confuse your dots and your dashes. Make it a true line. So if I do that, that means the iodine has 2, 4, 6, 7. It's got 7 electrons because it's in the 17th column. So when I make my Lewis structure now, oh, look at that symmetry. Everything is balanced. Everything is nice and symmetrical. It's really pretty electron density. And if we look at the electronegativity values for this, magnesium is a 1.2. I'm going to do it over here. And iodine is a 2.5. So the difference between these is 1.3. So we truly have a polar bond. Now, let's look at the direction of the electron flow. The iodine is 2.5, the magnesium is 1.2. So the arrow that we can show is electrons are being drawn toward the iodine because it has a higher electronegativity. In this case, my dipoles cancel. Therefore, we have a non-polar molecule. That's what's going on when the dipoles cancel. So we have to look at what's the electronegativity difference, draw the Lewis structure, put the dipoles into the Lewis structure, make them point toward, they can go in, they can go out. They're going to point toward the higher value of electronegativity and then see if they cancel out. In this case, they have to cancel. They're going 180 degrees out. That's going to give you a non-polar molecule. Now, this only works if you've gone through scenario A, single bond, and scenario B, lone pairs on the central atom. This is a symmetrical molecule. What if we change it just a wee bit? And instead of MgI2, what if we did MgClI? Now, all of a sudden, half the molecule stays the same, but half the molecule changes. And now we need those values. Mg is still 1, 2, iodine is 2, 5, and Cl is 3.0. So now I have the same dipole here, but the chlorine has a higher electronegativity value, and it has more of an electron pull. That's why I made the line fatter. It had a higher value. So would this molecule move? Heck yeah, it would. This molecule would experience a draw of electrons toward the left-hand side, towards the chlorine. The chlorine would be very electronegative in this case. And so what we have are polar bonds all about. Both of them are polar bonds. If they're both the same, just say, I've got polar bonds, and that's going to tell me, yeah, the whole molecule's got polar bonds. If they're different, then you got to tell me they're different. But if not, so then I look at this and I go, well, we also have a polar molecule. And that's what's going on. This is asymmetrical. This is going to be polar. Symmetrical molecules are nonpolar. Asymmetrical molecules are polar. One more example. And don't get caught up in this. Be careful. If I have my carbon in there, this is methane gas, CH4. It's one of the primary components in natural gas. And we already know 2.5 and 2.1. So we have 0.4 polar bonds. But because of the way we think, dadgummit, because of the way we think two-dimensionally, remember when I said 4, make it like that? H, 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 H. Now, I've got good symmetry. And this is 2.4. The arrows, bink, are all going in. Methane has polar bond. And because of the symmetry, dipoles cancel. I'm also going to have a nonpolar molecule. What if we what if we change it just a wee bit, make it asymmetrical? CH2 CI2 diiodomethane. Yuck. Okay, so electronegativity values 2.5, 2.1, and 2.5. So now our answer is I have a C, sorry, no, I can do that in red. I have a C to I bond. It's nonpolar. Electrons are equally shared. I have a C to H bond that's polar. And now we have to draw it. And because we're looking at it three-dimensionally like a tetrahedral here, it doesn't matter where you put them. We can try to balance it, but we'll do a model building exercise and make sure your iodines get their lone pairs. But this is going to have dipoles going in and in. The iodine doesn't have a dipole, it's nonpolar. This molecule is a polar molecule. So to wrap things up, just remember, A scenario is our single bond. Bond type is molecule type. B is lone pairs on the central. Lone pairs on the central make things polar. And C, if my dipoles don't cancel. That's another way of saying a molecule's asymmetrical. That's going to lead me to a polar molecule. It's a relatively complex topic that if you break it down into those three scenarios, you won't go wrong. That covers every molecule that we'll ever look at in this Gem Chem class. So my name is Smath. I hope this video helped you, and I look forward to seeing you in my next video.